Hello and welcome to today's class. For today, we're trying to proceed from where we stopped in our last class on chemistry. Last class, we considered the definition of atom, right? Having considered that, we discussed that whenever an atom is gaining electron, it is what the negative charge, and it's what whenever the atom is losing electron, is what the positively charge. We discussed about that last class. Last class again, we discussed about electronic configuration, right? And under electronic configuration, we discussed about two concepts there. Number one, there's KLMN shell concept and the SPDF configuration, right? So for today, I would like to start from SPDF configuration because in the last class we didn't actually finish the concept behind this, right? So let's start with SPDF configuration. By definition, SPDF configuration follows a pattern of number, which I'll be giving you right now. I should have go ahead to give you the formula for SPDF configuration, but mind you need to know how to derive the pattern of number for SPDF configuration, which I'll be giving you right now, right? So let's start with the SPDF configuration. For SPDF configuration, here's what you need to note. Your task there is to start with 1x, right? 1s, or perhaps um, somewhere closer. All right, I have 1s, 2s, 2p, 3s, 3p, 3d. Observe SPD, right? 1s, 2s, 2p, 3s, 3p, next up 3d, 4s, 4p, 4d, and 4f, 5x, 5p, 5d, 5f, right? And it continues that way, right? So your task here is that after writing this pattern of number 1s, 1s, 2p, 3s, 3p, 3d, 4s, 4p, 4p, 4d, 4f. This is like for the 20 element. You can say continue. You are free to do that, right? So after this pattern of number, what's next? Your next task is to take your left hand. Observe, this is my left hand. So left hand slant this way, right? So I'll take this one like this. Start with this. Next up, take with this. Next up, this one. I have this one, right? So let's start with this. So my first task is start with 1x, right? I'll start with 1x here. That becomes 1x. Next up, start with 1x. Next up, 2p. Sorry, 2x. I'll have 2x. Before now, 2x. This is the next one here. Start with 2p, then 3x. I'll have 2p, 3x. Next up, 3p, 4x. 3p, 4x, 3p, 4x. Next up, 3d, 4p, 5x. 3d, 4p, 5x, right? So this is like the pattern of number that SPDF follows, right? So at this point here, I want you to note something, right? The maximum element that each stuff can take here, S has the maximum element that it can take, P has its own maximum element it can take, and the others. So let's start with the maximum element each of them can take. So for X can take maximum just two elements. Sorry, electron, please. Electron, please, not element. Electron. P can take maximum 6 electron. D can take maximum 10 electron, and F can take maximum 14 electron. So those are like the maximum electron that each SPDF can contain. So S can contain just 2 electron maximum, P 6 electron, D 10 electron, and F I have 11 electron here. So these are like the this is like the concept behind SPDF configuration, right? Let's use this man here to solve some questions, right? So in our last class, we used some elements, right? Like hydrogen, sodium, and potassium. So my first element there is hydrogen. Example, I have hydrogen, that's H, right? Atomic number 1, right? So for my SPDF configuration, what's my SPDF configuration for hydrogen? That becomes, start with the first one. I have 1x. We said S can take maximum 2 electron, but hydrogen has just 1 electron. So just put the 1 here. So this is like the SPDF configuration for hydrogen, right? So the orbital, when it comes to SPDF configuration, we do work with orbital diagram. So the orbital diagram for this one becomes something of this nature, right? This is 1x to power 1, 1x to power 1. So we said a bus contains just maximum 2 electron. So I have just 1 electron here. So I'll start with the upper one this way. This is like the orbital diagram for my hydrogen. Let's take another example. Number 2, let's take sodium. Sodium, that's Na. Atom number what there? 11. So let's try to what's the SPDF configuration for sodium? All right, let's try to get the SPDF configuration for sodium. So for sodium, your task is quite simple. Just recall your pattern, this pattern here. So 11, right? And I'm having, start with 1x, please. So I'll have 1x. We said x contain maximum 2 elements, so I can put 2 here because I'm going to 11. 1x, next up 2x, I'll have 2x. 2 contain maximum 2 electron, I'll have 2 here. Next up 2p, I have 2p. P contain how many electron? Maximum 6 electron, 6. Let's see how many we have done so far. This is 6 plus 2 plus 2, that's what? 10. So I'm still left with 1 electron, right, to make it 11. So 2p, next up 3x, I'll have 3x. We said x contain maximum electron, but in this case I just need 1 more to complete 11. So this is like the SPDF configuration for sodium, right? So let's try to draw the orbital diagram. Now observe that I said that orbital diagram follow the diagram that its box, like a box, contains just 2 electron, right? This one is meant to be 2 electron, 1 up, 1 down. But in this case, I'm having just 1 electron. That's why I'm having just 1 electron in the box. So we said a box simply contains just 2 electron. Let's try to draw the SPDF configuration, the orbital diagram per se for sodium. The orbital diagram, you can draw it in 2 ways. Either you draw it in a staircase format, or you use a horizontal format, right? So I'll try to use staircase format. So look up, start with this. This is 1x, 1x squared. This is 2 electron, right? 2 electron. So I'll have 1 up, 1 down. I'm done with this for this one. Next up, I'm saying 2p, 2s squared. Take it this way. We said a box contains maximum just 2 electron. So this is 2x squared box. So just 2 electron, 1 up, 1 down. Fill the up one first before the down one. Next one, I'm having 2p6. Observe that I'm having 2p6. P contains 6 electron. And we said a box contains just maximum what there? 2 electron. So for 6, I need 3 box. In that case, let's say this is box 1 and box 2. This is 2p to power 6. Now I want to fill up 6. Start with the up one first, up one, then up one. Next, the down one, down one, down one. So this is 1, 2, 3, 4, 5, 6, 6 electron for this one. For ps to power 1, we said a box contains just what? 1 electron, right? This is 3x to power 1. I have the up one, not the down one. Start with the up one. So this is like the SPDF configuration for sodium. All right, at this point here, let's try to do you can just try to do potassium, right? You can try to do potassium on your own and try to draw the SPDF configuration for potassium. All right, at this point here, let's discuss something very important. Let's discuss valency, right? Let's discuss valency. All right, what is valency? Valency is simply the combining power of an element. It is important to note that for an atom to be stable, it must be duplet or it must be either duplet or octet configuration. By duplet configuration, we mean it must have two valence electrons. By octet configuration, we mean it must have just 8 valence electron. So we are saying that for an atom, either hydrogen, perhaps oxygen, sodium, calcium, either any of them, for them to be stable, it must have either what the duplet or octet configuration. We said duplet is what? Two electron in the atomos shell, right? Perhaps um right? Valence electron are simply the electron at the atomos shell of an atom, right? Or perhaps element, please, right? So what I'm trying to say is that in our last class, or perhaps in this class here now, we discussed about um, the hydrogen. I gave you hydrogen. I said the electronic configuration of hydrogen is just one. Number two, I gave you sodium, right? That's Na. The electronic configuration for sodium is 281, right? Number three, we did potassium, right, for KLM share concept in our last class. For potassium, that's K, right? That's 2881, right? Like this, like the electronic configuration for this element here. Now I'm saying the word valence electron. Now my question here is that are they stable? Right? That's like the question. Are they stable? For an atom to be stable, it must have either duplet or octet configuration. And I said by duplet, we mean it must have two valence electron. What are valence electron? Valence electron are simply the electron at the atomos shell, right? So it means that these ones here, this one here are simply the electron at the what? Outermost shell. When we draw the shell, right? Like this one hand out, this is KLMN, this is N shell, right? So it must, like this one now, potassium here now is not stable because I'm having just one electron at the outermost shell, right? So it's not stable. We said the condition for it to be stable is that it must be either 2 or 8. So this is just one, it's not stable, right? Potassium is not stable here. Sodium is N 281. It is not stable, right? It is not stable here. So if I'm writing sodium plus, if I write sodium and the positive sign there up there, this is sodium ion, right? So this plus, what does this mean? What does this mean? This is sodium. Is it gaining electron or losing electron? In this case here, because what the losing electron, we said atom or perhaps atom, yes, lose electron to become what the positively charged. So this is sodium losing one electron. Why? Because why is sodium positively charged? Because it's actually what wants to lose one electron. So it means that if I'm having sodium, one electron here, it is not stable. So for it to be stable, it will lose this one, then it will remain 2 8, and we said for 8 the condition says what? For octet configuration, right, it will be stable. They were said either duplet or octet. Now it will not become 2 8. It means that this 8 now will be at atomos shell. So this 8 now make it stable. So if I have Cl minus, this chlorine minus, right? So it means that chlorine too has one electron at the outermost shell. So if it this is chlorine minus, it means that chlorine is what, gaining one electron. So it means that when chlorine add one more electron to the one at the outermost shell, it becomes two, right? That's like the concept behind all this stuff you'll be seeing up of these elements, right? So like hydrogen, if I have H plus, this is what, hydrogen losing one electron, right? H plus. So that is like the idea behind all this stuff, right? So my aim here is to just teach you how to write, or perhaps how to name compound, right? If I say, yeah, write lead 2 triazonitrate 5, you should know how to write those stuff. That's like the concept. I'll try to show you how to write compounds, right? Using the concept of valency. All right, at this point here, I have to understand the charges here. So if I'm having Cl minus, it means chlorine gaining one electron. Sodium plus means sodium losing one electron. Those are the concept behind the stuff. And why are they losing and why are they gaining? Because what? To ensure that what, they are balanced, they are stable. And for it to be stable, it must have either duplex or octet configuration. All right, at this point here, let's discuss one important concept called radical. What's a radical? Look up, we said this plus, minus, what are they called? They are called what? Ions. So I can call this one chlorine ion, sodium ion, hydrogen ion. Why? Ion are what, the charges, either positive or negative, they are still what, they're still ion, right? So this is like sodium ion. Why? Positive charge up, so charges. So any element that have charges is called that element ion, right? Sodium ion, chlorine ion, and etc like that, sure. All right, let's discuss radical. What are radical, please? Let's discuss radical. Sorry, this is hydrogen. There's N here, please. All right, radical. Let's discuss radical. What are radical? By definition, radical is simply a group of atoms that act as a single unit, right? Two atoms combine together to form a single unit. Example, if I have H2O, this is water, right? But this is just two elements, hydrogen and oxygen, combined together to form what? A single, what can I call it? A single element per se, right? Because I said radical is simply a group of atoms that act as a single unit. So this one here comes together to act as a single unit, right? Example, CO3, triazocarbonate, right? This one too are simply radical. They are combined to form a single stuff there. Um, um, NH3. This is ammonium, right? Ammonium, right? So this is ammonium too. These are nitrogen and hydrogen combined together to form a single compound, right? So that's like ammonia, please, not ammonium. And ammonium is NH4. This is ammonia, NH3, right? So that are the concept behind radical. So let's take one line space paragraph. Some popular radical. So I'll be giving a table. Now that contains some radical, and we're using that table to write, using that table and the concept of valency and radical to write compound, or perhaps to name compound, right? Let me give the table, and we're good to go. All right, these are some popular radical and their valency here. So I have ammonium, that's NH4, -1 is the valency there. So I have -1 here. Next up, I have hydroxide, that's OH, -1, or perhaps 1 minus, please. It is 1 minus. I'll try to explain the reason why I'm having 2 minus, not -2. I'm having 1 minus, not -1, right? It's like it is meant to be -2, and I'm saying 2 minus. I'll explain the reason why. But your first task says that these are like the popular radical and their valency here. So we'll be using this idea here to write compound, right? So we're using all this idea to write compound. So make sure you have it on your medulla, right? Very, very important. This man here. All right. Why is it that I'm having 2 minus, not -2? right? The idea is quite simple, right? To differentiate between math and chemistry. That is why I'm having two minus here. Look up, if I have, let's say I'm having um, hydrogen or perhaps oxygen, being raised to the power minus 2, right? So pick out a scientist at random. Let's say a mathematician. If I call a mathematician, what are you saying here? A mathematician is saying um, 1 over oxygen squared 2. This is what a mathematician is saying, indices, right? So let me call a chemist at random, right? Let me call a chemist minus 2. If a chemist see this one, it means what? Oxygen gaining 2 electron. So this man here has two different meaning between two different scientists. So to avoid the confusion between which one is math, which one is chemistry, that's why when it comes to chemistry, you swap it. That becomes 2 minus, not minus 2. So this is chemistry. So if I'm saying something of this nature, this is no more math, it's not chemistry. That's like the idea behind the reason why I'm having 2 minus, not minus 2, and 1 minus, not minus 1. That's the reason behind that. All right. Let's now use this concept to write compound. So one line space paragraph, one line space paragraph, naming compound using the concept of valency.